All righty, great. Well, let's get moving here. So I like to start off with a little bit of story of just kind of illustrating why we want to use graphs and relationships to improve our machine learning. This is kind of an interesting situation where you would think voting and smoking, so two very different types of behaviors that actually have something in common as far as predicting outcomes. So we can actually, and there's been studies that have actually showed that we can predict whether somebody will vote or whether somebody will smoke based on their friends. And so whether their friends vote, that they are more likely or less likely to vote, and the same with the smoking behavior. What's even more interesting than that is even without a lot of personal information or demographic information about an individual, and looking at not just their immediate friends, but their friends' friends. So people they have not even met, we can very accurately predict whether somebody is likely to vote or smoke. So what those stories really show us is that relationships are very predictive of behavior. And there's been several books written on this. James Fowler wrote one called Connected several years ago. I love book recommendations. So I'll also say there's a couple other books about the power of friends. David Burkus wrote one called Friend of a Friend. If you're looking for your next opportunity, your next career change, that's a great book to understand how the relationships in your network can actually help move you ahead. The Formula by network scientist Barabashi also looks at how the relationships and patterns within relationships can actually be used for general success. So 3 really great books. If you're interested in this topic and diving deeper, lots of good material there. Contact information for myself and Jennifer here. And we're going to cover, we're going to look at graphs for predictions. We're going to look at connected features, link prediction specifically, and then we'll walk through a workflow for both Neo4j and Spark together.
Okay, so traditionally, there's a variety of ways that you can analyze, use data analytics, machine learning, etc. A lot of these are using traditional platforms like relational that are really good at storing lots of data, but sometimes crunching that and looking at different perspectives of that gets a little complicated. Kind of the next perspective on that is looking using big data technologies. We're really, really good at aggregating and filtering data, but a lot of times those queries can run really, really long, just trying to crunch all that data and aggregate everything. So this is where Neo4j comes in. It uses connected structures based on graph theory with nodes and relationships that show how your data is connected and how each of those individual points that you would have in a relational database or big data technology. It shows how each one of those points connects to one another. And so this is the structure that we're going to focus on today, using machine learning and link prediction with something like a graph database, a graph technology as the backend in order to help predictions. So graphs have really been growing in popularity over the last few years. If you guys are familiar with DB engines, it just kind of ranks based on the amount of content that's coming out and just shows the trends of different technologies. And as you can see, graph database has grown quite tremendously in the last few years. However, what also is really interesting is the fact that over the last few years, AI has also been increasing in popularity. So this is looking at different terms like graph neural network, graph learning, graph completion, embedding, etc. And just looking at the popularity and the number of appearances that these terms and these research studies come into play, and that is continuing to increase as well. So we're going to kind of bundle these two things together. The fact that both of these things have been growing in popularity, you can actually use them together in order to improve your predictions. So if you're familiar with machine learning, if you're working in that space now, you probably know that machine learning eats a lot of data. So it uses algorithms, trains software with specific example, and then learns from those examples in order to make better improvements and better predictions the next time around. So as you can continue to iterate on the massive amount of data that we already have, you get closer to that better score, that more perfect prediction, et cetera, and try to reduce those errors. But that means that you have to have a ton of data that just continuously adds up to have it be able to learn from what you already have and then make predictions on what might occur in the future.
So that's an interesting point, because I would say one of the things we hear from a lot of the data scientists we work with is, I never have enough data. If I just had a little more data, or if I just had a lot more data, I would be more accurate in my predictions. And so one of the things that graphs allow you to do is to use your the machine learning pipeline you already have, use the data you already have, but add in these graph elements to what you're already doing to increase the accuracy, the precision, and the recall you have. And that's because, as we saw just a few moments ago, that relationships are really predictive of behavior. Many of the models that we have today in data science ignore these complex relationships. They ignore the topology of your network. And so you're basically throwing out that data you already have, and we can add that in with predictive features to existing models, and even come up with some predictions that are based on relationships that you otherwise wouldn't be able to see at all. Now, there's a lot of different areas. You can, just see here that there's quite a different industries and areas where you could use graphs in data scientists, where people are using them in data science. One of the top ones that we talk to a lot of people about is financial crimes. So things such as fraud detection, understanding the patterns, really tightly knit communities that are tightly knit amongst themselves, but maybe not with the rest of the network. So little islands might be predictive of fraud. Anti-money laundering is another common use in financials. I won't go through all these, but another really interesting one is recommendations. So understanding where somebody is in a path of a buying cycle and being able to make a recommendation, not just on their past purchases, but also on their relationships, how they're likely to form communities, and that can inform more personalized recommendations. Another really interesting one is churn prediction. So if you have some kind of subscription service, you would like to obviously be able to predict if somebody's likely to not be a subscriber in the future and churn. But even more interesting, or in addition to that, which I find interesting, is what happens if somebody who's influential in the network? How do I predict somebody who's very popular or has a lot of influence might actually pull other people when they churn? So you might have a rippling effect. So a lot of different uses in various different areas, and we're going to look at how graphs can add to data science. In general, in big terms, we talk about helping people make better decisions with knowledge graphs, increasing the accuracy with feature engineering, and also more applicability and more trustworthiness with graph native learning. Today, we're going to specifically focus on graph feature engineering and increasing the accuracy.
Okay, so we're going to jump over and look at now what are connected features, and how do we go about using these. So there's just a basic definition of connected features. If you're familiar with machine learning topics, it's basically features that are coming from a graph structure. So it's connection related metrics about the graph, things like number of relationships going in and out of nodes, potential triangles and the numbers of those, or perhaps neighbors in common. So those are all things that rely upon data being connected in a graphic structure. How do we derive connected features then? There's a couple of different approaches you can use to this, and you can see kind of the spectrum on the slide. You have kind of the query end of things on the left-hand side, which is things like cipher queries, real-time local decisioning, pattern matching sorts of things. That's where you have a subject matter expert who knows what they're looking for and making that decision when they write the query and get the results back. So that's, you know what's predictive, or your subject matter expert knows what's predictive. On the other end of the spectrum, you have things like what we're going to talk about today, which is the graph algorithms libraries connected with machine learning practices that look at the entire network structure as a whole. And so looking at the overall structure and learning about that structure, how the network, how it updates, and then possibly predicting new structures or new connections in that. So you use the algorithms when you know that the shape is predictive, but you don't exactly know how. So graph feature engineering is basically tacking on some additional features that are graph focused. So if you look at the table that's down there in the right-hand corner, you can see our graph there on the left. And you might have some features like name, age, house, gender, whether the person is alive or not. So for instance, in our Game of Thrones data set that we use quite often with our algorithms, you can see we might have these fields in a traditional machine learning model. But the graph actually allows us to add a few additional features that might help us better predict certain things. So we could add something like character page rank, or their degree centrality, or the community that they might be a part of. Again, all those things are related to how that node sits in the graph and what's connected to around it. And then we can use those things to better predict, maybe based on what that person is connected to, that might actually predict a certain result or outcome better than the traditional features might. So you can use those to add additional features onto what you already have, and then help improve the predictions on that. So we have a variety of graph algorithms inside our algorithms library, Neo4j. This has grown quite a bit in the last year. We used to have just the top 3 areas, and we've since added the bottom 3 areas, probably in the last few months. So on the left-hand corner sitting there, we have community detection algorithms, several algorithms, and variants of those algorithms fall into this category, but it just looks at how groups tend to cluster together or how they tend to break apart. So how your data is partitioned into different clusters or different communities. The next one there is centrality or importance. This looks at individual nodes in the graph and tries to score their influence, their importance inside the network for each individual node. We run a lot of these algorithms. These are really interesting and fun ones to run just to see who might be kind of bridge nodes or who connects groups together. Pathfinding and search looks at the optimal paths or routes through the network. So things like shortest path or closeness centralities, trying to determine, or excuse me, that was a centrality. So pathfinding and routes, just looking at the best route. What is my optimal path through the network based on things like quality, or fastest, or efficiency, and of course all kinds of variants for those algorithms as well. The bottom section there, we're going to talk mostly today about the link prediction. So basically we have nodes in our graph that are not linked together, and we want to try to predict if those nodes will have a future relationship or a future link. And then all the way on the right-hand side there is similarity. So this does a calculation of nodes and says how similar are these two nodes based on the value, the results that come up from those calculations. And then finally, that gray one in the center is kind of one of our newer segments of our graph algorithms. It's a little bit more experimental, but we're starting to look at graph embeddings. So this is looking at representations of connectivity or topology within your graph. So this is where you start getting into the deep learning and the graph native learning.
Great. So let's take a look specifically about link prediction in general. And if we think about link prediction, we're trying to estimate, in the future, how likely is there to be a link, or is there something in our data that we're missing that should be there? And so you start with, usually a time element. You have a graph. time plus one, n plus one, what are the likely links, and you can kind of continue on that. So that's kind of in general, and it's usually based on a measure of topological closeness in a network, and that may not be physical closeness, it could be, but it might be closeness as it relates to strengths of relationships, numbers of relationships, weights of nodes, and things of that nature. So an example of how you might use link prediction that I really like is on a website, het.io. You can go in and check this out. It is HetioNet is the name of the project, but they have decades of biomedical data that is integrated into a knowledge graph. And then they use that information to look at drug repurposing. And so they use the structure of a graph to create features using graph algorithms and queries and various different methods to then try to predict a link between different genes and drugs and, well, it's genes and medical conditions and then potential drugs. So you can actually go online and search through this data. It's kind of a lot of fun to browse through it. But in this example on the right, you can see there's a gene, IRF1, and looking at multiple sclerosis, there is no direct path between that gene and that disease, but there is indirect paths. So we can see, going either through Crohn's or other genes, that there are indirect links. And so you can create features based on the structure of these indirect paths and then do machine learning to predict whether this gene with this particular drug interaction might actually be related to interactions or can be reused for a new disease. So you can repurpose drugs that are already approved. So it's just one example. When you're using graph algorithms, there's a couple different ways people use graph algorithms. There's general on the left, exploring, measuring, planning things in the future. You might have a certain score that comes out, maybe a similarity score, maybe a page rank score, and you might set a threshold and say, hey, if the number is above X, we're going to predict one way. If it's below X, we'll predict something else. So that's one way that you might use graph algorithms. In particular, for this talk, for feature engineering machine learning, what people typically do is they run those algorithms, they get their score or their label, and then they put it into a table, as you can see here, and then they do training on that table. And that's the process that we're going to walk through here.
Okay, so jumping into one particular example that we've used with this is predicting academic collaborations. So our use case here is taking a citation network data set from Arvin Minor, and so pulled in some data from there where basically it has 52,000 papers, 80,000 authors, 140,000 relationships between those authors, and then 29,000 citation relationships. So quite a bit of data there, but we dumped that data into Neo4j to create a co-authorship graph, looking at where we have particular authors that have maybe worked together on particular research papers or articles or other types of materials, and then ran that through connected feature engineering using our Neo4j graph algorithms, and then using something like Spark and MLlib to train and test a model using a random forest classifier. So we're going to actually walk through that process and kind of show how we did that and kind of what the results looked like. So on the next slide here, we have our link prediction workflow. So of course, you'll need to extract the data from a particular data source, in this case, from Arvin Minor, pulling all of those authors and then the articles that they wrote in. And then we'll look at kind of exploring that data, cleaning it up, modifying it as needed so that everything looks in somewhat decent order. Prepping all of that for machine learning. So this is where you figure out your features, things that might be predictive, and help you for that. And then training those models, evaluating the results, and then, of course, putting those into production. And this is not a generic one step to next step. As you can see here, there's some possible iterations where you might start a step and go, this doesn't look quite right, or I need to make some adjustments, and kind of go back a step or two and kind of reevaluate things or modify and fix things. So we'll kind of walk through this process and show what our data looked like at each point. So first up, we just import the data and create our co-author graph. Now we had to define a graph data model for this. So we needed to figure out what we wanted data to look like inside the graph. The data that was coming in was more in the format that's there on the top. So we have a particular article with a title and a year that it was published. And then we have two authors, potentially one or more authors, of course, that wrote that article and participated, contributed to that. And of course, you have author names. They have relationships that an author wrote a particular article or authored a particular article in this case. But we actually want to predict authors working with one another. So we don't really need the article piece necessarily. We just need to know we have a particular author that worked with another author on a research project. So we end up with the graph data model that's there on the bottom, where we have our author nodes and we have co-author relationships that link these authors work together, and then a particular year on that relationship to say at what point they worked together, what year they worked. So next look at, sorry, Amy.
Oh, I think I was going the same direction. Yeah, so next we started to look at actually creating some graph features on this, so doing our feature engineering. And of course, you know, before you start doing that, you basically do a little bit of analysis of your data. What's the distribution of different categories, even looking at time distribution. So taking a look at the data in general, just to see, is there some things that are uninteresting that you want to get rid of, or some sparse areas that that you want to de-emphasize, and just kind of looking for what you think might be predictive. And then you would go into the actual feature engineering. And for us, we played around with several different algorithms. I'm going to show you just a couple of them that we ended up using. Link prediction, as Jennifer said, looking at, you know, how likely is something to form a relationship in the future based on how structurally close it is. One of the algorithms we use is called preferential attachment, and that multiplies the number of neighbors between pairs of nodes. And that's a preferential attachment is a common concept in network science, where you're assuming that people with or anything with a lot of connections is more likely to gain more connections in the future. And that's the idea of the rich get richer, or the popular get more popular. And it's basically a measure of overall, what's the surface area of these two nodes, and how likely are they kind of to run into each other? If you think about large surface areas kind of running into each other, we can see in this graphic that if A, B, and C nodes, they're at the top, they currently don't have any links to each other. A and B, if we multiply the number of relationships they have, they're less than the multiplication of A and C. So we're going to therefore predict that A and C are likely to form a connection in the future, and not A and B. Another common measure is common neighbors, and that just looks at the number of possible neighbors in regards to triangles. So you can think of that as closing triangles. So A, B, and E here, we can see in the upper left, currently don't have a connection between A and E, but B is friends with both A and E. And so the idea here is that if we have friends in common or colleagues in common, we're more likely to be introduced. So that's just kind of more natural. So those are some that we use for link prediction. For community detection, we use triangle count and clustering coefficients. I actually found those in reading a lot of the research. You'll notice that they come up a lot in machine learning in general, and I would also say between link prediction. So triangles, if we just look at U here, and these measures are for the U node, just counts how many triangles go through U. Pretty simple. Clustering coefficient takes that measure and then looks at what's the probability that the neighbors of U are to be connected. And so that one for link prediction in general can be very predictive, and it's used a lot of times in just trying to understand whether communities are dense and likely to be connected. We also use Louvain modularity algorithm as well, and label propagation, which is another community detection algorithm. But Louvain looks at the interactions of communities and hierarchies of communities. It's kind of a nice algorithm in that you can dial up and dial down how tight or loose your definition of a community is. And so that kind of gives you a little bit of play with it. Label propagation also is another common community detection where we're adopting labels of our neighborhood as well. And so we use that one as well.
Okay, so now looking at getting ready to put this into our machine learning pipeline, we're actually going to run our train test split and then kind of figure out some sampling, some issues that we kind of ran across when we started this and how we kind of combated those things. So first up, our test train split. Why would you want to split your data? Well, first off, as you probably imagine, if you take all of your data and train your model based on that, and then you test your data on all of that, you're going to get a one-to-one accuracy, which means you're going to be correct all of the time, or if you don't, then you probably have a code issue, code bug somewhere. So you'll want to actually figure out, okay, take some of this data and train my model based on that, and then take other of the data and say, this is what I'm going to test that trained model on and see how accurate it comes out, how close it makes it. So we could use something like scikit-learn there on the next slide. You can kind of see the highlighted rows. So scikit-learn just has a random split. That's a lot of times how you'll end up dividing and segmenting your data, is just using some sort of random split. And so you see it's kind of done that on our table there with our columns. But what happens when we did that in a graph is that we actually ended up with a very, very kind of mistakenly accurate model. So we ended up getting something that we termed like data leakage. Did you have a comment there, Amy?
Oh, I was just going to say we were so excited the first round though. If you get if you're above 90% accuracy without any tuning, this is probably what's going on. Feels good for about 30 seconds till you realize it.
Yeah, false positive. That really can't be that good. So basically what happens in a graph is, as you can probably imagine, everything's reasonably connected. So when you start, when you do a random split, you're going to get some of this bleed over. You're going to have particular nodes and relationships that are segmented into the trained model, and others of that same network that might be pushed into the test model. And so therefore, you follow these nodes and relationships in and amongst one another, and you get this kind of bleed over of those two data sets. And so then it ends up predicting results that you've trained on already. So that's kind of the issue with that. So one way that you can combat this, and what we ended up doing, is to actually do a time-based split. So we segmented all of the data in the articles that were written before 2006, the co-author relationships that were written before 2006. We put into our trained model, and then anything equal or after 2006 for the co-authorships, we use that to test. So this is just one good way in a graph that seems to work pretty well if you can do a time-based split to go ahead and do that. So we ended up then using the relationships from the subgraphs as positive examples and compute the negative examples based on those subgraphs. So you can kind of see the diagram there. So that worked rather well. But there were some other issues we kind of ran into. So, and one thing that's kind of common with data sets is that you'll get some class imbalance. So in our particular case, makes a lot of sense. We have this data set where we have more authors who haven't worked together than have, which of course kind of makes sense. If most of your graph is already connected, then what's really the point in predicting much? You're not really going to get a whole lot of value out of that and be able to make too many more predictions before everything's connected. So what we had is this massive class imbalance. So as you can see there on the next slide, you could end up with something like a very high accuracy. So this image shows that you have a lot of blue fish, and predicting whether you'll end up with a blue fish or a red fish. You can see that 9 times out of 10, blue being the answer is going to be accurate. However, you're going to miss that 1 in 10 or 1 in 50 chance that you might have that you get a red fish and it's going to tell you to blue. So it can predict that a pair of nodes are not linked. So again, this class imbalance. Because again, most of the time it's going to be accurate, but you're not trying to predict that. You want to predict the things that may not be as common. So a couple of ways you can combat that is one by downsampling your data, and the other by upsampling your data. So downsampling basically strips out the larger data set and kind of cuts that data set down until it matches the smaller subset. Of course, the downside being here is you're cutting out potentially valuable information that could actually help you predict better. The other one there is upsampling, where you basically take your smaller data set and kind of multiply it up where it matches better the larger subset. Of course, the downside being here is you're duplicating the smaller data set and then ending up with duplicate results there that you're training and testing on. So I think we ended up downsampling for this. That seems to be the more common way to go. However, either one of these is perfectly valid. It's just what we ended up doing to kind of make that class imbalance a little more equal in our data set size.
Yeah, and I would be curious to hear from anybody on the call today, or even afterwards, if anybody uses hybrid approaches. So that's something I haven't done any research on, but kind of wondering if you could split these up in halves and then downsample, well, quarters really, but you could sample some and upsample some and then mix the results. So yeah, definitely some interesting ways to deal with that. The next, after prepping the machine learning, the next thing we need to do is, of course, train our models. And we definitely ended up doing some iteration on going back and modifying our features and trying to figure out what was more predictive. But we have to select our models, and we used a random forest for that in Spark, and then combined different elements as well. So, you know, as I mentioned, we used a random forest in Spark. If you're not familiar with that, this is just a nice visual of what a random forest looks like. So you basically have many different decision trees, and a decision tree just basically based on certain rules evaluates how it walks down the tree. It makes a decision. We were just using a binary classifier, so the decision was, does it have a link? Does it not have a link? A, B. Pretty simple. You just classify it, and then you let each tree, based on a different set of rules and objectives, basically do their classification. At the end of it, you vote. Whichever one has the highest vote wins. In this, with this visual classification, would be B. So pretty simple model. It's really a nice way to just get started with without a lot of if you don't have a lot of experience. So kind of a nice simple way to jump into it. For our particular model, this is just one decision tree, so you could see what some of that looks like. An example, starting out with a particular model, we were starting with the first step, and we were looking at common authors. So those were, you know, how many, you know, authors in common. Is it above a certain number? Is it below a certain number? What is the step that we need to take? Is it true? Is it false? In this case, in this step one, in our example, we had less than 1.5 common authors of scoring. So we went to step two. We were still false in step two. We go to step three. You can see on node ID 6, we're now looking at preferential attachment, making a prediction there, and we just keep walking through this logic until we get to a leaf node, till we get to our end location. In this particular example, the prediction was true, so we predicted a link. So pretty simple way to walk through and get started on making your classifications, especially if you're doing a binary classification. Now we did 4 different models and we layered them on each other. We started with that common author model, which uses the common author algorithm. We then created a model we called a graphy model, and that used common authors, but then it added in that preferential attachment, looking at that how popular you already are or how many co-authors you already have, plus the total number of neighbors as well. We then added in we added in triangles and clustering coefficients in a model called triangles. And then finally, we added a community model that added community detection algorithms using label propagation and Louvain modularity. Now we were testing our process and playing around, and you can see we're at each layer, we're adding in more algorithms and more features. If we were seriously scientific in our analysis, we might play around with adding in some of the features from the graphy model and the community model, but not the triangles model. And we might play around with different ways to group these models. As it was, we layered these on and then evaluated our results. Which brings me to evaluating the results. So of course, when you're going through this process and you're making changes, you're always looking at, do I have the, the accuracy and the precision? Do I have too many false positives? What is my predictive rates? We did those using some Spark tools, and this is a look at our initial model. So the first model with just common authors. At the bottom on the x-axis, you can see the false positive rate. On the y-axis, you can see the true positive rate. They're both obviously important. And the way that you see a lot of these ROC curves taken a look at is we're looking at the total score here on the bottom where it says random score, AUC 0.5, that's area under the curve. And so we want to maximize that area under the curve, because even with this common author model, we can see in the upper right, well, 0.86 accuracy, that doesn't seem too bad. Recall, and that's false positives, 0.75. So, maybe I've got not such great, maybe I have a few too many false positives, but overall it doesn't look too bad. But what really happens here is we've got false positives happening here in this top area and false negatives in this left area. So depending on how it's always better, the larger the number, the better in general on these, the AUC curves or the area under the curve. But you may want to tune your model for something in particular. So it may be something where you don't really care about false positives as much as you do about false negatives. You'd rather err on the side of maybe predicting something exists that doesn't than missing something that does exist. So you may have to tune your model for whatever it is you're actually trying to predict. When we did all 4, so this visual actually has all 4 models visualized here. By the time we got to that community model number 4, you can see in the lower right hand that we've gotten our accuracy, our recall, and our precision rates quite high, and we've also maximized the area under the curve quite significantly. So when you see this kind of to the left and up towards the bottom, pink curve is kind of where you're trying to get to on this. Now, when we evaluate results, we also have to look at the influence of different features. So one of the things that can happen is overfitting your data or your model to your data. And what that will result in is very highly accurate predictions for the data you trained on and really terrible predictions or not so good predictions on new data. And so what we usually do is kind of tune our features to not have too many features, so reducing the number of features but picking the most influential ones. And this is a plot that is using the Spark random forest averages, looking at the influence of the different features in the particular models. And so we can see here on the far left that the common authors, the Louvain, the label propagation, minimum triangles are all fairly influential to the model itself. So one of the things that you could do is play around with removing some of these features and see, does that reduce the predictive quality of my models? If it doesn't, that's probably a good indication that that you can remove those without degrading the model at all. This visualization is actually, as I mentioned, using Spark, but we also have users that use the PageRank algorithm to actually evaluate the features and look at which feature is more influential based on their PageRank. So again, something you would play around with, moving different features to different models, combining, removing, and kind of that iterative process that that Jennifer talked about. So this is just a all-up visual of what we've talked about today, kind of the workflow examples using Spark and Neo4j. You could use other technologies in a flow like this. And once you decide to actually put something in production, you might be doing something such as creating a recommendation engine, or a classification, or predicting links based on some information coming in.
Okay, so we're going to just wrap up with some resources here, things that you can actually do all of this analysis yourself. The results, the documentation, everything is available. So first up, we just want to mention our graph algorithms book that Amy and my colleague Mark put together. That is available at that link for free download still. So do go out and download that book. The last chapter talks about machine learning, and of course we have other chapters in there that cover all of the different areas of algorithms, with both examples in Spark as well as in Neo4j. Feel free to go out to our neo4j.com website, so you can spin up temporary, basically cloud instances using our sandbox there. It's that top link there. There's with some of them have graph algorithms already ready to go. They'll usually populate some test data sets for you to kind of play around with. There's no downloads involved, no strings attached there. Our graph algorithms, we have a guide out there on our /developer for that, and then online training. That we now have 2 free online trainings, one for data science and one for applied graph algorithms. Those are both available out on our Graph Academy page, so feel free to check those out if you want to know more and get some hands-on experience with our algorithms library there. The data and code from today can be found at that bit link. So that's the example from the O'Reilly book that we talked about today. And of course, please do feel free to reach out to Amy and me if you're watching this after, or if you have questions after this webinar. Please do reach out to us. Let us know questions or feedback or things that you've done that are really interesting. We'd love to hear from you guys too. So we'll turn this back over to Margaret and see if we have some questions from you all.
Great, thank you guys. Great presentation and lots of fantastic information. Because of that, we have many questions. And I've been trying to respond to everybody in the chat. So if I haven't gotten to you, I will get your questions, and we'll try and get as many answers to these in the final materials that will be shared out in the next day or so. So let's go ahead and start with one from Jason. This is just the first one that came through. And Jason was asking, can you talk about running algorithms against larger data sets, for example, 4 million rows and 500 variables?
Well, that's an interesting question. As far as creating algorithms, the algorithms that we used in this example were created for Neo4j by our labs team. So we were able to create those and implement them optimized for the Neo4j graph. So and that's allowed us to do some really quite large implementations, and we have some implementations specifically for, I believe we call them heavy graphs, but really large graphs. And we also have some link, I'm trying to think, on the developers page. So Under resources here, under developers, graph algorithms, there's links to some of our documentation that also talk about some configurations specifically for very large graphs. The other algorithms that are shown in this book for Spark were not written by us, but they were written by the community for either, either in machine MLlib or graph frames. And those are written, as I said, by the community to be used in that kind of distributed fashion. So as far as tips for writing specific algorithms, I think it really depends on knowing your data and knowing the platform that you're working in.
Yeah, and if you are dealing with Neo4j, you have your large data set inside Neo4j. Things that really can help is having a good amount of memory and a good amount of heap. So our algorithms, again, are optimized for our database structure, and they try to be as lean as possible, so that those algorithms run as best as possible over very large data sets. And we seem to have pretty good results with that sort of thing, but we do have in our documentation some ideas for optimizing and ways to kind of get an idea of what the memory it would take for certain algorithms, as well as some configurations you can set to try to reduce that even further.
Okay, thank you very much. Our second question is from Ernesto. What is the trend behind AI and DB performance required?
So thinking that's a big question. So when we talked about the early trend the chart that we showed early on was the amount of AI research papers that included graph in the title. So that was the trend number that we were talking about. And then as far as AI in general, I think Jennifer explained well, machine learning, how you train an AI system, does tend to take a lot of data to compute on. Anything you can do to optimize what you're doing, such as polling your graph features ahead of time and then computing your machine learning on that, on the features once they're now in kind of a table structure, will help. Most AI systems, if we're talking about the resultant solution, such as like a Siri or something of that nature, what we see there is you develop your model separately, and then you run your model for more real-time performance against something like a knowledge graph to help support making decisions. But I hope that answers the question. I don't know, Jennifer, do you have any other thoughts on that?
I think if you're asking what kind of bar we set for performance, I mean, obviously everyone's always going to want something faster. So our goal is to try to optimize and improve the performance of existing machine learning processes. So things that you're already running or dealing with to try to improve that performance and make those queries return faster, those results return faster. And then, of course, add the additional layer on top of that to have our graph features, things that are specific to the connected data. We do have some materials out there where we kind of show you we aren't looking to replace your existing machine learning model. We actually want to, using things like Spark, and Spark will support Cypher here in the next release, the upcoming release, where you can actually create kind of this graph layer in Spark and run a few of our algorithms on that to see, is this related, is this connected, is this quote graphy, and then to say, okay, let's push this over to Neo4j to actually use the optimized algorithms on Neo4j and push that into machine learning. So it's more of, you can kind of explore in what you're already dealing with. And then the things that are really connected need an optimized system for that. So it's not really something that Spark or other systems are optimized to handle. So that's where you would push that specific data over to Neo4j to help you calculate those features.
That's a good point, Jennifer. I think one of the things that I've heard, several of our engineers talk about is exploring your graph in Spark if that's where your data already is, and then building your product in Neo4j once you decided to keep the graph that you now know and love and want to do things with. Then you bring it over to Neo4j because it's optimized for that.
Oh, great, sounds good. Let's see, next question is from Arvin. I'd be interested in a follow-on discussion on knowledge graphs and graph-connected learning as well. So we will add that to the list unless you have some comments on that at this moment.
No, I think that's a great suggestion. Jennifer, go ahead.
Yeah, I was just going to say, just in the meantime, until we can get something spun up on that, we do have some, I believe, case studies and white papers and things already out on our website for knowledge graph. So we have quite a few use cases of customers using Neo4j for knowledge graphs. So there's probably some content already out there for that sort of thing, just to get you started. And then, of course, we're happy to provide additional materials or discussion or answer questions from there.
Okay, fantastic. Next question on the list. Have you done any work on entity alignment based on embedding and similarity?
So we are currently working on graph embeddings in general, and you probably saw that we have some similarity graph algorithms right now as well. As far as entity resolution or disambiguation, that is something that we have a lot of users ask about, and it's a use case for some of this machine learning that we're actively working on. But I don't believe, unless Jennifer, you know of a project I'm not aware of, but I don't believe we have any kind of a solution packaged for that yet. But it is something we're looking into, and it is kind of an active on our higher on our priority list, I should say.
We might have a blog post or a little bit of content out there where we've combined some of the similarity and embeddings, but I'm not for sure on that, so I'd have to do some digging to see if we have any current resources on that or not.
Okay, yeah, maybe we can follow up as part of the Q&A with, I think I know the blog post you're talking about, so we can do a little research on that, and maybe that'll give you a reference to look at, and then, as I said, more coming soon.
Perfect, I will add that to the list. Next question is, how do you determine the ground truth for predicting unobserved pattern in the graph?
Oh, ground truth. That's a hard question. So when we did our tests, Jennifer walked through, we did a time-based split, and that kind of gave us, we know the prediction, we know the links, excuse me, that are there. If you're doing, and then of course we try to predict them, in the future. One of the things that when ground truth comes up a lot, especially in machine learning, one of the things and I think we discussed this in chapter 8. If not, it's in the resources of this book. We give several reference sites for ground truth data sets that you can use for different situations. So the one caution I will say is that, as close as you can get to your domain. So ground truth for, retail is going to be so different than, ground truth for I don't know, service industry is going to be different than, biomedical or something like that. So close to your domain as possible. And the other thing, if you are picking a data set to look for ground truth, distribution is really important in graphs. So distributions of relationships. So graphs have a tendency to be very lumpy. You get these concentrations and hub and spoke structures. So if you're looking for a data set to be your ultimate, ground truth on your testing, getting one that has a similar distribution to nodes and relationships that you have is going to be really important.
Okay, fantastic. Next question. Am I restricted to just Spark? Can I use tools like Python or Alteryx for a specific type of data transformations as prep?
Absolutely, and I'm guessing Jennifer probably has more experience doing that than I do. But what we showed today was just kind of a template. What we did, we picked Spark because a lot of users actually have a lot of data in Spark, and they're trying to move from Spark to other analysis and to persist their information. Jennifer, do you have experience using some of these other tools?
Not necessarily specifically. However, Neo4j takes a variety of different kinds of input, so you can connect directly using Python and feed data over Python, scripts or how programs, etc., applications that you can use to feed that in. So yeah, again, Spark is just an example, but whatever tools you happen to be using. Neo4j has a lot of integration that it does really, really well at feeding data back and forth between different kinds of systems. So there's a way you can get data in and out, and if you already can get data cleaned up in other tools and then push that over to Neo4j, all the better, because then you don't have to mess with it whenever it gets into the graph.
Okay. And Jennifer, the integrations information, is that under our developer area of the website?
Yeah, we have a bunch of them there. GitHub is another good spot to check for integration projects. Some of them are community driven, though those will be a little bit trickier to find, but our community site might be in their spot where you can kind of see some of that stuff. So.
Yeah. And that's a good reminder. I didn't put it on the site, but we also have community.neo4j.com, which is our community website, a very active community. So as you come up with questions or just want to collaborate, that's a great place to talk about what you're doing.
Okay, fantastic. Next question, we just have room or time for this last one. Is it possible to assign attributes to the edge connectors? Can these attributes be more complex than, say, weights or direction?
So you can, Neo4j is a labeled property graph, and it does have, you can add attributes to the relationships. So an attribute could be not just a weight, it could be a date. In fact, I think in this example, we use the date as an attribute to the co-author relationship. You could, it could be anything. And you can also do things like look at similarity between entities based on different attributes as well.
Yes, actually, another interesting example of that is our Game of Thrones data set. Looking at the interactions graph, we calculate how many interactions occur between characters, and then we call it a weight property, but basically the number of interactions between those two characters that then get set as a property on that relationship. So yeah, Neo4j is flexible enough to have those attributes, those properties defined on nodes or relationships, however it's most meaningful to your model.
Okay, thank you very much, Amy and Jennifer. Really appreciate your presentation and your great answers to the questions that we've gotten through so far. We certainly have many, many more questions. I will curate those questions and get them over to Amy and Jennifer for some great answers that I'll put together in the full package. So thank you to the audience for joining us today. We'll be sending out this recording and all of the slides and other materials in an email if you're to the email that you're registered with, and you'll be getting that, I would hope, in the next couple of days. It'll take us a little time to curate all of this information. So thanks again, everyone, and have a great rest of your day.